MS Ramaya University of Applied Sciences.
Hi students, let us discuss. Steam Power Laboratory is part of Applied Thermodynamics Laboratory 2. It has the following experiments based on Rankine cycle. Determination of boiler efficiency, determination of dryness fraction, performance calculation of steam turbine, performance calculation of condenser. Industrial boilers are routinely used in process industries and power plants. The two main types of industrial boilers are fire tube boilers, water tube boilers. Small size boilers called package boilers have gained popularity in small industries for small capacity range with good efficiency. Small combustion space and high heat release rate resulting in faster evaporation. Large number of small diameter tubes leading to good convective heat transfer. Forced or induced draft systems resulting in good combustion efficiency. Number of passes resulting in better overall heat transfer. Higher thermal efficiency levels compared with other boilers. The Steam Power Lab has a package boiler from Firetech and the model is CT series. The boiler is a LDO light diesel oil fired boiler. It can produce steam at operating pressure of 6 bars and set point temperature of 200 degrees Celsius. The major components include feed water treatment, fuel tank, ignition system, reciprocating pump, temperature and pressure sensors and indicators, control system to maintain the set parameters, plumbing for steam output and regulation. The packaged boiler contains burner or ignition system, cladding and insulation, water tank and steam accumulator, multi-pass water tubes, multiple passes of flue gas, reciprocating pump to feed the boiler at specified pressure. The fuel energy can be considered to be 100%, out of which the flow of energy is divided as heat gained by boiling water, heat gained by superheater and reheater if present, heat gained by economizer and air preheater. The remainder of heat energy is lost to the surroundings. Loss due to moisture in air, loss due to moisture in fuel, loss due to combustion generated moisture, dry exhaust gas losses, heat loss from furnace surface. Unburned carbon losses, incomplete combustion losses, loss due to hot ash. Thermal efficiency of boiler is defined as the percentage of heat input that is effectively utilized to generate steam. There are two methods of assessing boiler efficiency. The direct method, where the energy gain of the working fluid, water and steam is compared with the energy content of the boiler fuel. The indirect method, where the efficiency is the difference between the losses and the energy input. The direct method is used to quickly find the efficiency of a boiler with the knowledge of the heat input and the heat output. Advantages of direct method. Plant people can evaluate quickly the efficiency of boilers. Requires few parameters for computation. Needs few instruments for monitoring. Disadvantages of direct method. Does not give clues to the operator as to why efficiency of system is lower. Does not calculate various losses accountable for various efficiency levels. Boiler efficiency is equal to heat output in steam divided by heat input from fuel. Indirect method is also called as heat loss method. The efficiency can be arrived at by subtracting the heat loss fractions from 100. There are reference standards for boiler testing at site using indirect method, namely British Standard BS 845:1987. USA standard is ASME/PTC 41 Part Test Code Steam Generating Units. The external surfaces of a shell boiler are hotter than the surroundings. The surfaces thus lose heat to the surroundings depending on the surface area and the difference in temperature between the surface and the surroundings. The heat loss from the boiler shell is normally a fixed energy loss irrespective of the boiler output. With modern boiler designs, this may represent only 1.5% on the gross calorific value at full rating, but will increase to around 6% if the boiler operates at only 25% output. Evaporation ratio means kilogram of steam generator per kilogram of fuel consumed. Reverse osmosis RO setup is used for the tertiary treatment of feed water. The RO process has a semi-permeable membrane through which water is forced. Additional treatment of water may be required to reduce the scaling. Reaction of kinetics of LDO is complex. A simplification can be made by considering the fuel to have an average chemical formula of complete combustion is assumed. 412 carbon atoms, 23 hydrogen atoms. Such a molecule, when it is completely combusted, requires 71 molecules of oxygen, producing products that contains carbon dioxide and water. The exhaust fumes will be at the highest temperature. It has the reaction, produces some amount of heat energy. With the available information, the packaged boiler efficiency in the indirect method is given by efficiency. Eta is equal to 100% minus loss due to dry flue gas minus loss due to formation of moisture from hydrogen minus loss due to radiation.
Hello students, here we are in the laboratory scale steam power lab, and we start out with the steam boiler. This one is a packaged boiler, and water supplied to the boiler is from the positive displacement pump, which you can see here, and steam pressure can be measured using this dial, and there is a temperature measurement at this point of the steam. Steam from the boiler is filled up in the accumulator. This one is the accumulator, and from the accumulator the steam passes through and goes to the turbine, and in between we have the steam flow meter, and after the steam flow meter we have the separating calorimeter. This is the separating calorimeter, and from the separating calorimeter we have the throttle calorimeter, which is shown here. Steam from the boiler is fed to the turbine, and after the turbine produces work, the spent steam is sent to the condenser. This one is the steam inlet, and this one is the steam outlet. We have a separate water inlet and water outlet, so it is a shell and tube type heat exchanger. The power generated by the turbine is fed to the dynamometer, and the load on the dynamometer is measured using this load cell. All the data from the load cell is shown in the control panel. Let us start with the first experiment, which is boiler efficiency calculation. For boiler efficiency calculation, we work with our packaged boiler. To start up this boiler, we have to have enough RO water. We have a RO water plant, which is shown here, and the water tank is on the outside, and we need to check the water level in the water tank. And next to the RO plant, we have the diesel tank, storage tank. Diesel from the tank is connected to the boiler through this unit. Before we start the boiler, we need to open the overflow valve and close the steam flow valve. Open the overflow valve completely and close the steam flow valve completely. Boiler is turned on starting with the main power supply, and consecutively we can switch on the main panel using this switch. Here we can see that the set point temperature for the boiler is 200 degrees centigrade, and at present the water temperature is 25 degrees centigrade. Using this switch, we can turn on the positive displacement pump, which pumps water to the boiler. So initially we are going to turn it on to the 1 position. When the switch is in 1 position, the positive displacement pump pumps water to the boiler, and from the boiler water overflows and goes to the tank. When water overflows, we can put this switch to the 2 position, and this switches on the burner. Observe that the water temperature increases steadily. When the temperature of water reaches around 85 or 90 degrees centigrade, the pressure can be seen in the gauge. At this point, we are going to close the overflow valve. At this point, the pressure inside the boiler starts building up, and we are waiting till it reaches somewhere around 5 or 6 bars. When it reaches 5 bars, we can open the valve. Pressure in the accumulator starts building up, and we are going to let the steam to the turbine. Record the boiler water temperature, and further calculations for the boiler efficiency can be done. This completes the boiler efficiency calculation experiment.
Let us discuss. The steam produced by the boiler at Steam Power Laboratory has a quality that needs to be determined to understand the energy potential of the steam. Although dryness fraction is not a state property, it is often used for wet steam to find the enthalpy and entropy values. The quality of steam produced by boilers depend on a variety of factors like temperature set point, pressure at which steam is tapped, heat loss in the supply pipes, the location of steam tapping along the circuit, the use of superheater. Just a measurement of temperature and pressure will not give an accurate measurement of quality, particularly in wet steam region. The steam produced is close to saturation limit, and in certain conditions it may be still wet steam. Experimentally, we are going to ascertain the quality of steam using calorimeters like separating calorimeter, throttle calorimeter, separating and throttle calorimeter. Quality of steam is a ratio of mass of dry steam to the total mass of steam. Steam quality is measured using instruments known as calorimeters. Separating and throttle calorimeters are routinely used to check the quality of steam. X dryness is equal to mass of steam divided by mass of water plus mass of steam. The separating calorimeter consists of outer shell and an inner perforated metal cup. The steam is tapped from the main steam supply and enters the separator from the top. The steam is forced to make a sharp turn when it hits the perforated cup on any other mechanism that produces the same effect. This results in a vortex motion in the steam, and water separates out by the centrifugal action. The droplets then remain inside the separator and are collected at the bottom, where the level can be recorded. However, not all the water droplets remain in the collector tank. Some water droplets pass through to the condenser, and hence this calorimeter only gives a close approximation of the dryness fraction of the steam. If we have steam that is nearly dry, we make use of a throttling calorimeter as shown in the figure. This calorimeter is operated by first opening the stop valve fully so that the steam is not partially throttled as it passes through the apparatus for a while to allow the pressure and temperature to stabilize. If the pressure is very close to atmospheric pressure, the saturation should be around 100 degrees Celsius. It may be assumed that the steam is superheated. When the conditions have become steady, the gauge pressure before throttling is read from the pressure gauge. After throttling, the temperature and gauge pressure are read from the thermometer and manometer respectively. The barometric pressure is also recorded. If the steam whose dryness fraction is to be determined is very wet, then throttling to atmospheric pressure may not be sufficient to ensure superheated steam at exit. In this case, it is necessary to dry the steam partially before throttling. This is done by passing the steam sample from the main through a separating calorimeter as shown in the figure. The steam is made to change direction suddenly, and then the water, being denser than the dry steam, is separated out. The quantity of water which is separated out is measured at the separator. The steam remaining, which now has a higher dryness fraction, is passed through the throttling calorimeter. With the combined separating and throttling calorimeter, it is necessary to condense the steam after throttling and measure the amount of condensate. If a throttling calorimeter only is sufficient, there is no need to measure condensate, the pressure and temperature measurements at exit being sufficient.
Now let us move on to the dryness fraction experiment. For the dryness fraction experiment, we are going to find out the pressure in the separating calorimeter, the pressure in the throttle calorimeter, and the corresponding temperatures, and we are going to measure the amount of steam coming out from the separating calorimeter. Now collect the water from the throttle calorimeter. Take down the pressure measurement in the separating calorimeter and also the pressure measurement in the throttling calorimeter. This completes the dryness fraction calculation for steam.
Let us discuss steam turbine. A steam turbine is a power-producing turbo machine that converts steam power into mechanical rotation at the shaft. The performance of steam turbines is measured by a variety of performance index, of which thermal efficiency and isentropic efficiency are calculated in steam power lab. A set of rotor and stator blades rotate when it comes in contact with steam. Observe a worker inspecting the rotor blades. The high pressure stages have smaller diameter row of blades, and as the pressure decreases in subsequent stages, the diameter of rotor increases. The picture shows the maintenance of a typical steam turbine. Notice the maintenance worker in the picture stands on the stator assembly. Also, observe the typical dimensions of the steam turbine in a typical power plant. Based on the type of steam interaction, we divide the steam turbines into impulse and reaction turbines. Steam turbines can be compounded to regulate the power production and speed of rotor. The different methods of compounding are velocity compounding, pressure compounding, pressure velocity compounding. Velocity compounding. Steam loses its kinetic energy to the rotor while passing through more than one rows of moving blades. The pressure drops across in nozzle and steam reaches its maximum velocity at nozzle exit. The velocity then reduces over two or more rows of moving blades separated by guide vanes. As the high-speed steam passes through the stages, it loses its kinetic energy to the moving blades and its velocity decreases. Guide vanes are fixed to the casing and facilitate smooth exit of steam from preceding rows and smooth entry to successive rows to avoid losses. There is negligible loss in guide vanes owing to friction. Pressure compounding. The pressure energy of steam is converted to kinetic energy in more than one stage. The first partial drop in stem inlet pressure occurs in the first row of nozzle where pressure energy is converted to its kinetic energy. The steam passes through first row of moving blades where it loses its kinetic energy to the rotor and its velocity reduces. The steam at moderate pressure then enters second row of nozzles, also act as guide vanes, where its remaining pressure energy is converted to kinetic energy, causing the velocity to rise again. The steam at moderate velocity then enters second row of moving blade, where it loses its kinetic energy to the rotor. At second stage, pressure compounded turbine is shown in the figure. At the end of the second stage, the pressure has dropped to exhaust or condenser pressure when steam leaves the turbine. Pressure velocity compounding. Pressure compounding with two-stage velocity compounding in between. Two-stage velocity compounding gives more efficiency than three-stage. The first partial drop in stem inlet pressure occurs in the first row of nozzle where pressure energy is converted to its kinetic energy. The steam passes through first row of moving blades where it loses its partial kinetic energy to the rotor. It is followed by guide vanes and second row of moving blades where remaining kinetic energy is utilized. The steam at moderate pressure then enters second stage. The second row of nozzles also act as guide vanes, converts its remaining pressure energy to kinetic energy, causing the velocity to rise again. Similar to first stage, the kinetic energy gained is utilized in two rows of moving blades. A pressure velocity compounded turbine is shown in the figure. At the end of the second stage, the pressure has dropped to exhaust pressure when steam leaves the turbine. The performance of steam turbines is measured by a variety of performance index of which thermal efficiency and isentropic efficiency are calculated in Steam Power Lab. Isentropic efficiency of a steam condensing turbine. The isentropic efficiency of a turbine is a comparison of the actual power output with the isentropic case. The steam turbine at the lab is a second stage reaction turbine. Typical speed of operation is about 4000 to 6000 rpm, recommended to operate below 5000 rpm.
Now let us continue with the efficiency calculation for the turbine. The turbine can be started by suitably opening the valve, which allows the steam to go through the turbine and the spent steam goes to the condenser. To calculate the turbine efficiency, we suitably open the valve and feed the steam to the turbine, and from the steam the turbine starts rotating. The spent steam goes to the condenser. There is a pressure measurement and temperature measurement at the inlet of the turbine. There is a pressure measurement and temperature measurement at the outlet of the turbine. The pressure at the outlet of the turbine is vacuum pressure. After the turbine is running, the actual measurement is taken in the control panel. we can take the different temperatures by selecting in the channel selector. The temperatures are indicated here. The turbine speed is indicated in RPM in this indicator, and the turbine load using the dynamometer is set using this dial and is indicated over here. We take different readings based on different loading settings, and we record the obtained speeds of the turbine. This completes the turbine efficiency calculation. Now let us go to the condenser efficiency calculation.
Let us discuss steam condenser efficiency. Steam condensers are an essential part of Rankine cycle-based power plants. It delivers the condensed steam to the feed water pump for the boiler. The condenser efficiency is one of the performance parameters for steam condensers. Condensers may be classified broadly into two major groups according to the manner in which the cooling water cools and condenses the exhaust steam. These are jet condensers and surface condensers. Jet condensers, in which cooling water comes in direct contact with the exhaust steam and the steam as a result is condensed. The condensing or cooling water is usually sprayed into the exhaust steam so that rapid condensation of the steam. Surface condensers, in which the cooling water and exhaust steam do not actually mix. The cooling water passes through a number of tubes while the exhaust steam passes over the outer surfaces of the tubes. The most common type is a surface condenser, which has the great advantage that the condensed steam is not thrown to waste but is returned to the boiler through feed water system. A jet condenser is a much simpler and less costly apparatus than a surface condenser. The jet condenser should be installed where a cheap source of boiler feed water is available. Surface condensers may be subdivided into surface condenser, in which exhaust steam passes over a series of tubes through which the cooling water is flowing. The evaporative surface condenser, in which exhaust steam passes through a series of tubes and water is allowed to flow in the form of thin film outside the tubes, while air passes upwards outside the tubes. These are some of the major differences between jet condensers and surface condensers. In general, jet condensers are lower in cost but require smaller quantity of water. But surface condensers are expensive to install and need a large quantity of water. In a steam condenser, we have a mixture of steam and air, and the total pressure which exists in the condenser is the sum of the partial pressures exerted by the steam and air. With no air present in the condenser, the total absolute pressure in the condenser would be equal to partial pressure of steam corresponding to the temperature of condenser, and maximum vacuum would be obtained in the condenser. The ratio of the actual vacuum obtained at the steam inlet to the condenser to this maximum vacuum or ideal vacuum, which could be obtained in a perfect condensing plant with no air present, is called the vacuum efficiency. There is no standard method of determining the efficiency of a condenser, but a method adopted by the well-known makers of steam turbines, Mrs. Parson and Company, has been widely used in engineering practice. By this method, the thermal efficiency of a condenser is stated as the ratio of the difference between the outlet and inlet temperatures of cooling water to the difference between the saturation temperature corresponding to the absolute pressure in the condenser and inlet temperature of cooling water. Air pumps. The primary function of an air pump is to maintain vacuum in the condenser as nearly as possible equal to that corresponding to the exhaust steam temperature by removing air from the condenser. Another common but not essential function of the air pump is to remove condensate together with the air from the condenser. An air pump which removes both air and condensate is called a wet air pump, while one which removes the moist air only is called a dry air pump. Figure shows a schematic of Edwards air pump. Steam jet operated air ejectors are almost universally used for the production of high vacuum demanded in modern land condensing plants, owing to their simplicity, the small space occupied, and the absence of moving parts with the consequent reliability.
Now let us start the condenser efficiency experiment. In this experiment, we are going to measure the temperature at the turbine outlet and temperature of steam which is coming out of the condenser. We are going to measure the temperature of inlet cooling water, and we are going to measure the outlet cooling water temperature. The condensed steam mass flow rate can be measured using measuring the outlet of the condensed steam. This completes all 4 experiments in Steam Power Lab in MSRUAS.
At MSR, you mark your imagination.